Okay, welcome to the last lectures on functional programming. To be more precise, today is the last lecture on functional programming. So the plan for the future is on Wednesday there will be nothing. Well, nothing means no exercise course, no lecture. On Friday there will be the last lecture. And Friday means July 6th. And then there will not only be the last lecture, there will also be the last exercise sheet. And then the week after, there will be no lecture anymore, but there will be one last exercise course related to this exercise sheet that we will distribute here. And so the week after, Monday, nothing, Wednesday, nothing. So it's almost holiday, but not quite. So on the last Friday, which is the 13th of July, there will be the last exercise course. And then there's holiday. So that's the plan. And what will be the content? Well, the content of the last two lectures and also of the last exercise sheet is the last chapter of the lecture, namely type checking. So this is what we are going to discuss today and also on Friday. So the last chapter is type checking and type inference. So what's the goal? Well, as you all know, Haskell is a typed language and it's statically typed. So that means during compile time, the program is checked for type correctness, and if it's not well typed, then the compiler rejects this already. And otherwise, no type checking has to be performed during runtime anymore. And in that way, it is similar to other statically typed languages like Java, which do the same thing. So they also do type checking while you compile the program, and then afterwards, in principle, no type checking has to take place anymore. So Haskell, like many other languages, is statically typed. So that means when we compile the program, it is type checked. And so type checking takes place during compile time. And then at runtime, you don't have to be afraid anymore that there could be type errors, because, I mean, if your program has been checked, then everything is guaranteed to work well. So not during runtime. And, well, what's the advantage of static type checking? The advantage is that many errors are detected before your program is actually executed. So, I mean, this makes sure that these errors are already detected when you compile your program. And if there's a type error, then the program gets back to you and you have to repair your program, and it's not even executed. So this guarantees to avoid at least certain mistakes which would otherwise occur in your program. And so what does that mean? What's the workflow if we want to compile Haskell programs? I mean, we didn't only introduce the syntax and the semantics in the lecture, but we were also concerned with the implementation. And the implementation could now work as follows. So how would our implementation of Haskell work? Well, we would start with full, or at least with complex Haskell. Then we would automatically translate it to simple Haskell. And this would be automatically translated further to Lambda calculus. And we know that both of these translation steps are they preserve not only the semantics, they also preserve the types. So in other words, if the term that comes out here is well typed, then and only then is the original Haskell program well typed as well, and also the types are maintained. So if this term that you get here has type int, then your original Haskell expression also had the type in. So this preserves both the semantics and the types. So preserves the semantics and the types. And so once we have compiled a Haskell program to Lambda calculus, we can do the type checking then for Lambda calculus. So we don't have to care about type checking for the many, many Haskell constructs. We just do type checking for the Lambda calculus, which is this tiny little sublanguage of Haskell. So then we do type checking. And if type checking works well, so afterwards we know for sure that this Lambda term is well typed, then afterwards we execute it. So then we really do the execution. And if type checking fails, I mean, if the type checker says this is not well typed, we will not execute it, but we will stop immediately. So that's the idea. This is the workflow. And we know all of these steps except this one. We don't know how to perform type checking automatically. And obviously this has to work automatically because your Haskell compiler does that as well. So it should be possible to do this automatically. And how this is going to be done, well, that's the goal of this chapter. And we will do this in 2 steps. We will first define the necessary constructs and do this step by step. And then we put all the components together to get the type checking algorithm. So let's introduce the notions that we need. And the notions that we need are type schemata and type assumptions. So type schemata and type assumptions. Okay, the main problem with type checking in Haskell is polymorphism. So the main problem is that we have type variables. If we had a monomorphic program, then it's pretty easy. I mean, you have functions, they have certain types, you have arguments, and either the arguments are of the correct types or not. So it would be very easy if we had no polymorphism. So the main problem is polymorphism. So this is what makes type checking interesting in Haskell. So this means that if you have one expression, then this expression in fact has many types. So one expression has many types. And for an illustration, let's look again at, well, let's suppose we have defined lists ourselves. So we have this declaration for the data type lists. So there are 2 data constructors, nil and cons. Nil for the empty list and cons for the non-empty list. So cons takes an element of type A and another argument of type list A. And now the question is, what is the type of nil? So what is the type of nil? Well, we would expect our type checker to return the answer, well, the type of nil is list A. Now, it's a list with arbitrary contents. So the elements in the list may have an arbitrary type A. But of course, you can also use nil at places where you expect a list of integers or a list of booleans. I mean, that's perfectly fine. So it has the type list A, but you can also use it whenever you need a list int or a list bool or list anything. So all of these are, in some sense, types of nil, because if you need an argument of one of these types, you can use nil. And, well, if you look at these types, you can see, well, this is the most general type. So if you have a type variable in a type, then the meaning is this expression has this type for any possible instantiation of the type variable. And, of course, we want our type inference algorithm to compute this. And then we know, well, any variable can be instantiated by anything. So this is the most general type of nil. And this means the meaning of these variables in the types, the meaning is that you can instantiate them in any way you like. So type variables can be instantiated arbitrarily And no matter how you instantiate them, they give you another type of this expression. And to make this more explicit, that these type variables really stand for an arbitrary type and you can instantiate them in any way you like, we introduce the notion of type schemata. And a type schema is something like a type, but we make it more explicit what these type variables mean by adding quantifiers for type variables. So to make this more explicit, we use so-called type schemata. And, well, type schemata are something like this. So the type schema for nil would be the following. It would be list A, but we want to make explicit that this A can be instantiated in an arbitrary way, and therefore we add this quantifier here in front. So the type schema for nil is for all A, list A. So this is the universal quantifier, meaning for all types A, this is a valid type for nil. So we make these, we add these quantifiers, and they, why we need them, we will see in a few minutes. So the universal quantifier means, or for all A means, that the variable A can be instantiated arbitrarily. Okay, and now what's the goal? The goal is for every Haskell expression, well, Haskell, no, we will do this only for the lambda calculus. So for any lambda term, we now want to find its most general type schema. So the goal is for any lambda term, T, infer its most general type schema. And well, what are lambda terms? Lambda terms are variables, constants, applications, and lambda abstractions. And if we have a constant, let's say, for example, the constant not. Now, not should have a certain type, namely, it should be a function from bool to bool. And how do we know this? Well, because for these predefined operations, we know already the types. So, I mean, if you recall how we did this when we defined the semantics, we had this environment. And in the environment, we had already predefined the semantics of all these predefined operations. And for the types, we do something similar. So we also need, well, built-in information which tells us what the types of predefined operations are. So for the constants C, so C was the set of constants in the lambda calculus, we need built-in or predefined information on their types. So this is similar to the semantics. When we defined the semantics, where we needed built-in information on, well, on the semantics, where we needed built-in information on their meanings for these constants. And this, when we defined the semantics, this built-in information was stored in the environment. So here we had environments. And for the types, we don't call this environment, but for the types, we call this type assumption. So for the types, this built-in or this predefined information this predefined operation is stored in a so-called type assumption. Information is stored in a so-called type assumption. So in some type assumption A. And what A does is A is a mapping. A maps any constant from C to the corresponding type schema. So, and if you remember how we did this in the semantics, we started with an initial environment. And this initial environment contained all the information for predefined operations. And here we do something similar. We now start with the predefined, with the initial type assumption, and then this type assumption will later on be extended. So we start with an initial type assumption, and this really only contains information on the types of the predefined operations and the variables. So an initial type assumption, which we call A0. And this initial type assumption containing information on the type schematas of constants and variables. On the type schematas type schemata. I should either write schemata or schemas, but schematas is really wrong. Containing information on the type schemata of predefined operations of Haskell, and they were stored in this subset C0. So this was a subset of the constants on the type schema of predefined operations and of variables. And well, for every variable, this initial type assumption gives us the same information. Namely, so for every variable x, this initial type assumption tells us what is the type of x. Well, what is the type of such a variable? For which types can I use it? Can I use x for integers? Yes. Can I use x for booleans? Yes. I can use x for anything. I can use x for any possible type. So such a variable x has the most general type possible. So the most general type would be just a type variable a. But now we deal with type schemata. And so whenever we have a variable, a type variable that can be instantiated arbitrarily, then we make this explicit by adding a quantifier. So the type schema for a variable is this, for all a.a, or for all b.b. It doesn't matter how you call this variable, but it means that you can instantiate this thing arbitrarily, and it can have an arbitrary type. And well, for the operations in here, for the operations from C0, it depends. Well, their type is predefined. So for example, if you have not, that's a predefined operation of Haskell. And not only the semantics of not is predefined, but of course also its type. And the type of not is a function from bool to bool, for example. Or suppose we have something like this. Now, to make life easy, we disregard type classes. So we attempt that there are no type classes, and the plus function on integers is different from the plus function on floating point numbers. And this plus is a shorthand. Well, it's not shorter really, but it abbreviates the predefined plus function, but I want to use this as prefix notation. So this should stand for the predefined plus function on integers, and then the type of this is also predefined, namely it takes two integers and gives me back an integer. And if I define lists myself, like I did up there, what would be the type assumption for nil? So what would the initial, if my program contains this data declaration up there, where I define the data type list with the data constructors nil and cons, then what would be the most general type schema for nil? Well, the type for nil, the most general type would be list A. And I want to make clear that this A can be instantiated arbitrarily. So it's for all A dot list A. And if I want to have the initial, if I want to know what's the type of cons, well, if cons is defined like this, then obviously it's a function that takes an A, a list A, and it returns a list A. And in here, I can instantiate A arbitrarily. Okay, so this is the idea of these type assumptions. So let's define this formally. So this is the first definition, where we introduce type schemata and type assumptions formally. Type schemata and type assumptions. So let's define the grammar for type schemata. So type schemata are defined by the following grammar. And this is almost the same as the definition of types. Because, I mean, the only difference between a type schema and a type is that, well, a type schema is a type, but in addition, you may also have quantifiers. That's it. So let's recall the definition of types in Haskell. So this is an old slide. So today, barbecue. And oh, you have grasshoppers at the barbecue. So that sounds very delicious. Okay, so this was the definition of types in Haskell. And the definition of type schemata is almost the same. The only difference is that you can also have quantifiers. So how would the grammar look like? Well, it would look almost like this. So if you want a type schema, how can you get it? You can apply a type constructor to n already existing type schemata. So you can take a type constructor and apply it to type schema 1 ... type schema n, where n is greater or equal to 0. And then there are some type constructors predefined. So predefined lists we ignore because then we would have to treat an extra case all the time. So let's not look at predefined lists. If you want lists, then you can also define them yourself like I did above. But there is the arrow, for example. So if you have two type schemata and you write an arrow between them, then you have a new type schema. So you could take one type schema 1, arrow type schema 2, that's again a type schema. Then what else do we have? We can build tuples. So that's also possible for type schemata. So you can take type schema 1 dot 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 type schema n, where again n is greater or equal to 0. Then for types we also have the possibility to use a variable. So that's also possible. And there is one extra case, namely you can always quantify variables. So whenever you have a type schema, you can add for all and then some type variable in front of it, and that's again a type schema. So that's the only difference apart from that type schema and type is the same. And in particular, every type is also a type schema. So you don't have to quantify every variable, but you may. So a type schema is a type where certain variables can be quantified, where some or none or all variables can be quantified. And if a type schema contains a variable that is not bound by a quantifier, then we say it's a free variable. And we had this concept of free variables already several times. And sometimes it's nice to have a notation where we add a quantifier for all the variables that were free up to now. So if we have a type schema with certain free variables, so let's move this upwards to get some more space. So for a type schema, tau with the free variables a1 to an, if we just write a universal quantifier in front of this type schema without writing any variables here, this should be a shorthand, an abbreviation for the following, so that this denote the following type schema where we simply add universal quantifiers for all the variables. So for all a1 dot, for all an dot tau. So this is just a short notation because sometimes we want to add quantifiers to bind all the variables that were not bound up to now. So this is the definition of type schema. And now we also define type assumption formally. And a type assumption is just a mapping from variables and constants to type schemata. So the idea is for every variable and constant, we want to, the type assumption tells us what is the most general type of this variable or of this constant. So a type assumption A is, and it doesn't have to be total, so it doesn't have to tell us the types for any possible variable or any possible constant. So it's fine not to be defined for every variable or constant, and that's okay because I mean this results from a Haskell program, and your Haskell program is finite, so it doesn't contain all the variables and all the constants that we need, and so the type assumption also doesn't have to be defined everywhere. So it can be a possibly partial function from the variables and constants to the set of type schemata. And if this type assumption is only defined for finitely many arguments, then we have a short notation for it. So a type assumption A where the variable or constant xi is mapped to the type schema tau I for all I between 1 and n, which is undefined otherwise, which is undefined for all other arguments. Can also be written in the following form. Then we just write the following. We write it like a set, and well, the set says x1 has the type schema tau1, x2 has the type schema tau, x2 has the type schema tau2. Well, that's difficult, and xn has the type. Whatever, it has tau n. This is the type schema of x1, xn. Okay, so this is the meaning of type assumptions. And we start with an initial type assumption. This initial type assumption tells us the type schemata of predefined operations and of variables. The initial type assumption A0 so this is the initial type assumption is defined as follows. And well, see slide. I don't want to write this all down now, but instead I brought a slide where I wrote it down. So the initial type assumption, how is this defined? So the purpose of this initial type assumption is to give us the types for predefined operations and variables. So let's start with the variables. Well, for every variable, I mentioned this already, the initial type assumption tells us that this variable can have an arbitrary type. So the corresponding type schema is this one for all a.a, meaning that this a can be instantiated by any possible type. Now, if we have a predefined operation, so something from C0, and C0 contains all the predefined functions like not or square root or plus or whatever, all the things that are predefined in Haskell, well, also the type schema, the corresponding type schema has to be predefined. So this has to be stored in this initial type assumption. So for example, as we saw it up here, the initial type assumption says that not has the type bool to bool, or plus has the type int to int to int, and so on. Now what happens if we have data constructors, which might be user-defined? Well, suppose we have a user-defined data structure that looks like this. So suppose the user defined the following data structure. There is a new type constructor, type_constructor of arity m. So it takes m type variables. And then it has several data constructors. And one of them is called constr. And this data constructor has arity n. So it takes arguments of type 1 to type n. And now the question is, what is the type of constr? Or what is the most general type schema belonging to constr? Well, that's clear. It should be a function which takes n arguments of these types and gives you back a result of this type. That's written here in the next line of this definition. So the initial type schema for such a data constructor would indeed be the following type schema. You take arguments from type 1 to type n, and this is the result. And all the variables, all the type variables that occur here, namely A1 to AM, they have to be universally quantified. And now I use this short notation where I just write the quantifier in front and no variables, and that means bind all the variables, quantify over all the variables. Now, where else is this initial type assumption defined? Well, it has to be defined on all the function symbols that we introduced in this translation. Because, I mean, in reality, we want to implement Haskell. So we had this translation from complex to simple Haskell and from simple Haskell to lambda calculus. And for these translations, we had to introduce some additional predefined functions. For example, a function bot. So what should be the type of bot? Well, bot stands for undefined. So it's like a function which is defined by the equation bot equals bot. So the type of this is completely general. The type of this would be A, and A can be instantiated arbitrarily, so we get, again, this type schema over here. Now, what about if? If is also a predefined function. What's the type of if? Well, if takes 3 arguments. The first one is Boolean, and the second and the third one are arbitrary, but they should have the same type. And the result of this if is, again, either the then argument or the else argument. So it should have this term at this type. I take a Boolean argument, and one for the then case and one for the else case. And then depending on the value of this first element, I get something of type A. Now, maybe a bit more interesting is the type of fix. What do you think is the type of fix? Now, fix was a predefined constant, and it is used whenever we translate recursively defined functions to the lambda calculus. So fix takes a function and computes its least fixed point. And it behaves as if it were defined by the following equation, namely fix f equals f of fix f. Now, if you define something by this equation, what would be the type of fix? Well, let's suppose that, this f, this must be a function somehow. So this must have the type A to something else. And if it has a fixed point, then the argument type and the result type has to be the same. So this should have the type A to A, this f. So this also has the type A to A. And then we can see what the type of this is, because f only accepts input arguments of type A. So the result of this must have type A. Otherwise, we cannot apply f to it. So in other words, fix takes an argument of type A arrow A and returns something of type A. So fix takes a function from A to A and gives us the least fixed point of this function. And the least fixed point of this function must also have type A. So it takes such a function and gives us the smallest argument that is a fixed point of this function. And, well, is a construct. That was one of the functions that we introduced to get rid of pattern matching when we went from complex Haskell to simple Haskell. So that was a function that checks whether an argument of this data type was built with this data constructor. So it takes arguments of this data type, and depending on whether this argument was built with this constructor or with a different constructor, it returns true or false. So the result is a Boolean. And we had an argov construct function as well. So this has the following type. It also takes an argument of this data type, and provided that the argument was built with this data constructor, it returns the tuple of the arguments of this data constructor. Now this data constructor is defined like this. So the arguments of this data constructor have the types type 1 to type n. So the result should be a tuple with n components of type 1, type 2, type 3, until we reach type n. And we had some more. We had these selection and tuple functions. So there's a selection function which takes a tuple of, if it's cell ni, we take a tuple with n components and select the ith component. So this works, the type is a function that takes a tuple with components a1 to an, and it returns the ith component. So the ith component has the type ai. And there is this tuple function as well, which produces tuples. So this takes n arguments and returns a tuple of these n arguments. So this should be the type of tuple n. And we had an isF function as well for tuples. So the isF function only takes tuples with n components and returns, well, if it's really a tuple with n components, it returns true. So this is not very surprising. These are the types that these predefined functions have. And they are all stored in this initial type assumption. And we will start type checking with this initial type assumption, and then we will probably modify it during the type checking. And one more thing, if we have, I mean, you remember for environments it was similar. We started with an initial environment, and then sometimes we had to modify this environment. And to do this, we defined the plus notation on environments to override parts of environments. And we use the same notation also for type assumptions. So if we have two type assumptions, so for two type assumptions, A and A prime, we define a new type assumption A plus A prime as follows. And this is exactly the same idea as for the environments. So if we want to know in this new type assumption what is the type schema for X, then we first look into type assumption A prime. And if type assumption A prime is defined for X, then that we take this type schema. And only if A prime is not defined, then we look into type assumption A. So this is A prime of X if A prime is defined for X. And otherwise we take A of X. So this will be needed to extend type assumptions and to override certain parts of type assumptions. So these are the basic things that we need to know. These are the notations and concepts we need. And now we can construct the type inference algorithm. So we get into the last subsection of the lecture. We will now really build a type inference algorithm which automatically infers types and which automatically checks whether terms are well typed. Okay, so we now introduce the type inference algorithm. So we have seen that if we have a term, then we cannot just determine its type in isolation, but the type depends on the type assumption. I mean, if your term contains plus or not, then whether your term is well typed or not, or also the type of your term, depends on what not and what plus have as a type. So type checking always takes place with respect to a type assumption. So type checking is performed with respect to a type assumption, and therefore the algorithm that we develop, the type checking algorithm, has two inputs: the term that we want to type check and the type assumption. So the type checking algorithm, and this type checking algorithm has the beautiful name W. So the type checking algorithm W for historical purposes. So this was invented by Robin Milner and related people, and they called it W. I don't know why they called it W, but it's called W. At least it's short. So the type checking algorithm W has two inputs: the term T, a term T, well, that's the term that we want to type check, and we want to find out what is this well typed, and if yes, what is the most general type of T? So a term T, so should be checked for well typedness. typeness, and if it's well typed, then its most general type should be computed. Should be computed. And the other input is a type assumption. So a type assumption A. And this type assumption tells us what are the types of the occurring functions, the occurring constants, and the occurring variables. And what's the result of W? So of course the result of W should be the type of the term T. So W has in fact two results. So one result is what we expected. We wanted to have the type of this term T. So this type is some type T. So type tau, and this is indeed the most general type of T if T is well typed, otherwise the algorithm fails. And moreover, it has a second result, and the second result is a substitution. A substitution theta. And the meaning of this substitution theta is that it tells us that T is only well typed if we refine the current type assumption by this substitution. So for example, in this type assumption, we might have the information that some variable x has type A. And it might turn out that your term is only well typed if x had not type A but type int. And that would mean that in order to make T well typed, we have to refine the current type assumption, x has type A, to the new type assumption, x has type int. So this substitution, this tells us that T is only well typed if the type assumption A is refined to the type assumption where we replace all free variables in A according to the substitution by replacing all free type variables in A according to the substitution theta. So in other words, we say that A must be refined to the new type assumption A theta, or you might also write theta of A. And the meaning is whenever there's a free type variable in this type assumption, then theta tells us that this type variable, this free type variable, has to be instantiated. Otherwise, T would not be well typed. We will see how this works in examples. And now let's try to come up with this algorithm. So the goal is we have to define how this W algorithm works. So W gets these two inputs, the type assumption and the term. And it produces two outputs, the substitution, which refines the current type assumption, and the type of this term T. And we will now define how this algorithm works by looking at the different forms of the terms. So I mean, this is a lambda term, so it's either a variable, a constant, an application, or a lambda abstraction. So let's regard these cases and define how W works in all these different cases. Yes?
What's the difference between A theta and A plus theta? You define this plus operation for that.
Yes, but I defined the plus operation for type assumptions. So type assumption is a function which maps constants and variables to type schemata. And I can extend this function by another function. So I can write something like A1 plus A2. And this, for example, might say x has the type tau1 and y has the type tau2. And this could say, well, x has the type tau3 and z has the type tau4. And if I put this together, I get a new type assumption. And in this new type assumption, I do everything as A2 says it, and only if A2 is not defined, I do what A1 says. So x would have the type tau3, z would have the type tau4, and for y this is not defined, so for y I look here, so y would have the type tau2.
And that is just a variable substitution. It isn't.
Well, it's not a variable substitution. It's you mean what the difference is between instantiating type assumptions by substitution and extending it by plus. Okay, then let me illustrate that. That I can, and I understand what you mean. So suppose that A is the following type assumption. Let's say the variable x has the following type for all A dot AB. So the type variable A is quantified, but the type variable B is not quantified. And now theta is a substitution which says B has to be replaced by int. Then A theta is, well, it's the same type assumption, but all free occurrences of B have to be replaced by int. So now x doesn't have this general type up there anymore, but now it has the type A goes to int. So this is what I mean by substituting type variables. Okay, so now the goal is let's define this W algorithm, and we look at the different forms of T, and we do this step by step. So let's first look at the easiest case, and the easiest case is T is a variable or T is a constant. So this is the easiest case. Let's call this section 4.2.1, type inference for variables and constants. Type inference for variables and constants. So if we want to find out the type of a variable or of a constant, well, we simply look into the type assumption. So to determine the type of a variable or a constant of a variable or constant C, we look into the type assumption. So let's say A is our type assumption. So if we want to find this out, so suppose that the type assumption for this variable or constant C is something like this. So it looks like this for all A1 to AN. So this is a shorthand for all A1, for all A2, for all A3 to for all AN, tau. So if this is the type schema for C, so this is what this type assumption tells us, then from this type schema we now have to produce again a type. So we have to get rid of these quantifiers again. And suppose that these are all the quantifiers that we have. So tau has no quantifier anymore. So where tau is not a type schema, but a type. So that means, in other words, it does not contain quantifiers. It doesn't contain quantifiers anymore. So all the quantifiers are in front, and this is the part without quantifiers. Then the most general type of C is, well, it's tau. But if we leave it like this, then these variables a1 to an, they could occur in tau. I mean, most likely they do occur in tau. And we don't want to raise any conflicts, because maybe we use the same names for type variables elsewhere as well. And so we rename these type variables to be on the safe side. We rename them to fresh type variables that we didn't use before to avoid any kind of name conflicts between the names of these type variables. So let's replace A1 by B1. So this is again a substitution where the type variable A1 is replaced by B1 and AN is replaced by BN, where B1 to BN are fresh type variables that we didn't use before. Where B1 to Bn are fresh type variables that we didn't use before. And this is done to avoid conflicts if these other type variables A1 to AN occur several times. If A1 to AN occur several times. So this will be the type of C. And, well, do we have to refine our current type assumption? We only refine the type assumption if this is needed to make the term well-typed. Well, if the type assumption says this thing has this type, then C is well-typed, so there is no need to refine the type assumption in any way. So we don't refine the type assumption. So the type assumption does not have to be refined because our term C is already well-typed without refinement. Does not have to be refined. And that means that the substitution theta that we get as the second result is just the identity. So the substitution that we get as the second result is the identity, and it means this is the identical substitution which replaces everything by itself. So how would that work in examples? So what would the W algorithm give us if we start with the initial type assumption and we want to know what is the type of X? And X is a variable. Well, we know that A0 of X is the following type schema. It's for all A dot A. So what we have to return is we have to return this type here, this A, but all universally quantified variables are replaced by fresh variables. So, for example, by B. So replace all occurring A's by B's, and so we get B as the most general type of X. And we don't have to refine this type assumption in any way because X is already well-typed. There is no need to refine anything. According to this type assumption, X is well-typed. So no further refinement is needed. We just refine it by the identity, which means we don't refine it at all. Or if we want to know what is the type of not, well, we look into the type assumption. The type assumption tells us the type of not is bool to bool. Now here there is no universally quantified type variable, so no need to replace anything. So the type of this is bool to bool. And again, the type assumption is not refined further. And if we want to know the type of cons, for example, Well, again, we look into the type assumption. The type assumption tells us that cons has the following type. It has the type A to list A to list A. And here A can be instantiated arbitrarily. And so if we want to know the most general type for cons, we take this type here, but we replace all occurring A's by something fresh, for example, by B. Now you can see that it's good that we replace things because maybe later on we would get conflicts because we have an A here and an A there. We will see later on what would go wrong if we wouldn't do this replacement. So let's replace it by a fresh variable that cannot harm, and then the type would be, for example, B to list B to list B. So in the type inference algorithm, we now get the following. So let me construct this algorithm step by step on the slide. So the type inference algorithm, what does it do? Well, it needs as input a type assumption and a term. And the term is a lambda term. So it comes from the set of all lambda terms, which we denote by capital lambda. And, well, what is the result if I call W with A and T? Well, either T is well typed under this type assumption, and then the result will be a pair like this. So the most general type of T, and this refinement, which tells us how A must be refined in order to make T well typed. All the computation fails. Well, why it can fail, we will see later on. And now the first case was that we have a term like this. So C is a constant or a variable. And then the W algorithm is defined like this. So what does this mean? This means our type assumption looks like this. So in our type assumption, C has the following type. So this big type assumption here with this plus means for C we get this type, the type tau, and quantified with A1 to AN. And for the other constants and variables, we get whatever A may tell us. So that doesn't really matter. So this means this is the case where our type assumption here tells us that C has this type schema, A1 to AN dot tau. And then what is the type of C? Well, we get tau, but we have to instantiate, we have to replace A1 to AN by fresh variables. So we get tau, but A1 is replaced by a fresh variable, B1, and similarly for AN. And there is no need to refine the current type assumption any further. So this is the first and easiest case of the type inference algorithm. It simply looks into the type assumption and gives back whatever the type assumption tells us. And the interesting cases are what happens if the term is more complicated. So if the term is a lambda abstraction or an application. So that's the next question. And well, before solving this, let's create some more space. Okay, so the next step is type inference for lambda abstractions. So now we have to compute the type for a term like this. So the goal is to determine the type of something like this. So something like this, lambda x dot t. And now, of course, now what is the idea? How would we do this? Well, the obvious idea is let's first determine the type of t. And then when we have the type of t, it's not so difficult to come up with the type for the whole term. But of course, the problem is that this x can occur in t. I mean, that's also quite likely that x will occur in t. Because, I mean, this stands for the function that takes this argument x and returns this result here. And then most likely the argument will occur in the result. So how can we do this? Well, the idea is we could assume that x has some arbitrary type, b, And under this type assumption, we could then determine the type of T. So the idea is the following. Assume that X has some arbitrary type T, B, arbitrary type B. And well, assuming this, that's not so difficult because we have type assumptions. So what we can do is we can simply add the type assumption. We add the assumption X has the type B to our type assumption, to our current type assumption. And then under this assumption, under this new assumption, we determine the type of T. Determine the type of T, and let's say the type of T is tau of T. And if we did that, then we know what the type of the whole term is. Then the whole term has the following type. Well, what's the type of the whole term? If T has the type tau and X has the type B, then the whole term has the type, it's a function from B to tau because it maps arguments of type B to results of type tau. So that's the general idea how we could do this, but we have to be a bit careful because there can be some complications. But there can be some problems or complications. And to show you that, let's look at the following nasty term. So let's look at the following nasty term. This nasty term takes a function f, and, well, it will add certain things, so there's a plus. Namely, it adds the result that I get when I apply f to true with the result that I get when I apply f to the number 3. So this is a bit ugly because, well, this waits for a function f, and it seems that I can apply f both to Booleans and to integers. And the result of f should be an integer because I have to add this. So, I mean, plus should be applicable to it. So the result of this should be an integer, and the result of this should be an integer as well. And the question is this well-typed or not? And how can I write this? How can I detect whether it's well-typed or not? So the function f must be applicable both to Booleans and to integers, to both Booleans and integers and ints, and its result must be an int. Must be of type int. So what do you think? Is this well-typed in Haskell? So can you write, I mean, in Haskell you can write down this term. I mean, okay, you cannot write lambda, but you can write backslash. So if you write this down in Haskell, is this well-typed or not? Would Haskell? No. Okay. Well, in principle, it should be possible to apply functions to different arguments. So, I mean, there are functions that you can apply both to Booleans and to integers. Yes, true. Still, no, so yes, there are functions that you can apply to both Booleans and integers, definitely. So for example, the function lambda x dot 1, which takes an argument, ignores it, and returns 1. This you can apply to Booleans, this you can apply to integers, and its result is an integer. So this would be a function like f. You can apply it to true, it gives you 1. You can apply it to 3, it gives you 1 as well. And 1 plus 1 is 2, so that looks nice. So after this information, who thinks that this term is well-typed in Haskell? Very few people. Who thinks that this is not well-typed? Also very few people. Okay, so the majority is abstain. Well, okay, then you at least cannot say anything wrong, but also nothing right. So this is not well-typed. Surprisingly, this is not well-typed. And why? Why is this not well-typed? Well, the problem is that what would be the type of this big expression? The problem is that I can only apply this. I mean, this is a lambda term. So I can only apply this to f's, which themselves are applicable both to Booleans and to integers. So in other words, this f must have the following type. Well, it must be applicable to anything. So it must be applicable to integers or to Booleans, and it must return an int. And this must work for any a. So this must have the type schema like this. So for f's, I can only enter functions which are really applicable to anything, to Booleans and to integers, and in fact to everything. So such functions do exist. So indeed, the function that I just mentioned, lambda x dot 1, this thing really has this type. So this really has the type schema for all a dot a goes to int. So yes, such functions do exist in Haskell. And if I apply this term up there to this thing, everything will work well, and I get the number 2. But now what is the type of this big expression up there? So the expression up there, lambda f plus f true f3. Well, what type would it have? It would have the following type schema. Well, clearly the result of this thing is an integer, because plus always gives back an integer. And so this plus thing here, this has type int. And this f here, well, this has the following type schema, namely the one up there. So I can apply this to any function with the following type for all a dot a goes to int. And now you can see that this type schema looks different from the type schemas that we had before, because now this quantifier here is not at the outside, but it's somewhere inside. It's inside this argument of the arrow. And that makes a difference. Oh, now I need more space. So what is the difference between the type that we have here? So it's a function which can only be applied to functions which themselves are applicable to any possible type. So what's the difference between this on the one hand and a goes to int goes to int? So these two type schemata are not the same. Here the universal quantifier is in this argument, and here it's outside this argument. So what's the difference? This means if you have a term which has this type, then it automatically also has the same type whenever you instantiate a by anything else. So this means every term of this type also has all the less general types that I get by instantiating a by any possible type. So this also has the types well, if I instantiate a by int, then I, for example, get int to int goes to int. So I can apply this thing to functions that map only integers to integers, or I can also apply this to functions that map booleans to ints. So an example for a term with this type would, for instance, be the following thing. Lambda f, let's try to make this similar to the other term. So again, plus. So the result of this thing will be an integer. And now for f, I can use any function from int to int, or any function from bool to int. So it should be, any of these functions should be admissible for f. So I have to apply f to something which is both an integer and a boolean. And there are not many things that satisfy this. So for example, bot satisfy this. So I can use bot whenever I expect an integer. I can also use bot whenever I expect a boolean. So it's no problem to apply this function here, for example, to the square function. The square function takes an integer, gives you back an integer. If you apply square to bot, that's fine. It will be undefined here as well. So, well, undefined is of type A, and therefore you can use it also at places where you expect an integer, and so that would be admissible. So this term really has this type. But here it's different because, I mean, here I could apply this to any function from int to int, and also for any function from bool to int, and I would not get a type error. Whereas in this term up here, if I apply this to any function from int to int, then I have to apply the function f also to true, and then I get a type error. So I cannot use any function from int to int for this f on the blackboard up there. I can only use functions that can be applied both to booleans and to integers. So that really makes a difference. And now you can see why we need these quantifiers. Without the quantifiers, I could not make a difference between this type schema and this type schema. But this is a type schema which is acceptable in Haskell. So, I mean, this term here is well typed in Haskell. And this is a type schema that is not acceptable in Haskell. I mean, that term up there has a certain type schema, namely that one, but Haskell doesn't use these type schemata. And, well, what's the difference between these two type schemata? The difference is that the quantifier is not on top level. So as soon as the quantifier occurs somewhere inside the term, then this is not admissible for Haskell anymore. And these type schemata are called not shallow. So this type schema is not shallow. And shallow means that unifiers may only be on the very outside and nowhere else. So this type schema is not shallow, flach in German. And that means the quantifier is not at the outside. And most programming languages don't allow these forms of type schemata. And the reason is that if we allow them, if we would consider terms like this well typed, then type checking becomes much more difficult. Because whenever you want to apply this term up there to a function, you have to check, is this function applicable to any possible type? And if you do it like that, then type checking becomes undecidable. That means that you may have your program, but your compiler cannot find out whether it's well typed or not. That's undesirable because you want your compiler to type check your program, and it should say yes or no, and should do this even reasonably fast. And therefore, these kinds of types are excluded in most programming languages, including Haskell. So such type schemata are forbidden in most programming languages, including Haskell. In most languages, and the reason is we want to make type checking decidable. To make type checking decidable. And that means for Haskell, this term up there is not well typed, because in Haskell we have no non-shallow type schemata. So let's define this. What's a shallow type schema? So we say that a type schema is shallow if it has the following form. If it has the form, the quantifiers are only at the very outside. So for all a1 to an, and then after the dot, there are no quantifiers anymore. So where tau contains no quantifiers. No quantifiers. So in other words, tau is a type, not a type schema. And well, this is the reason why this term up there is not well typed. And in the next lecture, we will finish this type inference algorithm, and we will determine how to infer the type schemas and the types for Lambda abstractions and for applications. So see you on Friday, and on Wednesday there is no exercise course and no lecture.